Hello, my name is Anjali and I'm doing my PhD in cognitive science from IIT Kanpur under Professor Nishit Srivastav. The paper I'm presenting you today is a commentary on how much a realistic model of choice should be able to predict. To get a peek into how much a model can predict, we'll take a look at a quantitative measure of completeness given by Freudenberg and team in their recent paper. Completeness of a model is a measure of how close the model is from an ideal model. But then what is an ideal model? Let's take the case of a simple binary classification model and three features with two possible labels, hate and like. When an individual is asked to state preference for apples, here is the list of possible labels. An ideal model in this case can achieve perfect accuracy with this dataset. However, preferences of the individual change over time, like in this case. And when data has inherent variance, even an ideal model will be correct only, say, 75% of the time. Or we can say there are limits to the predictive accuracy for an ideal model when data is noisy. And this is what we call predictable variance. Deploying this principle, Freudenberg and team formalized the concept of completeness of a model as the ratio of error difference between a random predictor and the model predictions with the maximum possible error difference. Reiterating in terms of error variance, predictive error of an ideal model forms the lower error bound of any model. Now we are equipped with this tool. Let's see how much a simple model of risky choice behavior stands up to this measure. But before that, let me quickly give you a brief background on the risky choice behavior. Risk in choice behavior is implied by the level of measurable uncertainty in a given decision problem. An individual will be risk-seeking if she selects more uncertain option. A typical paradigm to study risk behavior in decision making is by way of certainty equivalent task, where risk is spread over outcomes as shown in this example with decisions from description. More generally, it can be represented as this for two outcome risky choice options. All the problems in this study follow this task paradigm. Freudenberg et al. Evaluated the completeness of CPT, cumulative prospect theory, formalized by this equation, which predicts that people choose the option with maximal subjective utility. As you see, this model uses the prospect features along with 5 free parameters to predict the choices. The dataset used by Freudenberg and team is the Bruhin and team dataset, which considered 8906 elicitation of 50 risky choice problems using certainty equivalent paradigm in DFD, that is decisions from description format. When measured for completeness, CPT is 95% complete. This means any model trying to improve over CPT has only a scope of about 5%. Now that we know how CPT fares in explanation of choice behavior, we will search for models which have been able to improve upon CPT theory using the same set of features. A bit of a background before that, Technion Choice Prediction Tournament was organized by Irrev and team in 2010. The basic idea of this tournament was to build better models of explanation of risky choice behavior with the model evaluation criteria as predictive accuracy with minimum errors. An important implication of this is that the focus is entirely on the quantitative parameters of explanation, while the qualitative parameters like theoretical soundness, simplicity, and elegance go into the background for model evaluation. Thus, models become source of prediction than explanation. Process-wise, the organizers released a dataset called estimation dataset based on certainty equivalent paradigm and posted it on web along with fits from several baseline models and invited other researchers to compete to predict the results from a second dataset called competition dataset. And here are the results for the decisions from description format. The baseline model is the cumulative prospect theory, which explained about 70% of the total variance in the dataset. On the other hand, the winning model, which is a logistic regression of prospect features and expected value difference with a total of 7 parameters, explain about 90% of the total variance. That's a significant improvement. Now let's look at what mean squared distance for these models tell us. This here is the MSD or mean square distance of the cumulative prospect theory for two data sets. Using Freudenberg and team's measure of completeness for CPT and assuming a random predictor of 0.5 for binary choice, we measured the error of the ideal model plotted here. Remember, error of any model cannot be less than that of an ideal model. Finally, we compared this with the MSD of the winning model, and this is what we got. The winning model has been able to reduce much more error than what an ideal model could do. How can any model be better than an ideal model? This gave us an impetus to empirically find out how much variance can be realistically explained by a computational model. What we saw so far, given the observations of human choice preferences, a computational model predicts the choice behavior. The correlation between them gives us the variance that a model is able to explain. In our study, we ask humans to be their own models and see how they can predict for their observed behavior. That is, we see how their preferences change over time. This variance we propose should be the upper limit of any model trying to do the same job. And so if V1 is greater than V2, it indicates some qualitative issue with the computational model. Here's the design of our study. We took the estimation problem set of Techno Choice Prediction Tournament consisting of 60 problems. For each participant, we split the problem space into 4 equal parts. Each week, we present the problems to the participant in the configuration presented here, where A and B subsets are repeated after a minimum gap of 1 week to discount for the memory effects, while subsets C and D are interspersed with a repeated elicitation of the problems. We conducted 2 experiments in our study following this 2-outcome certainty equivalent paradigm. The first one used one-shot decisions from description format as illustrated before, where probabilities were laid out explicitly. And the second experiment used decisions from experience format, where probabilities are not explicitly defined, but the participant is allowed to sample them as much as they wish to, without consequence, before committing to an actual choice with consequence. 58 participants, of which 19 were females, completed the DFD experiment, that is, decisions from description, without compensation and feedback. For DFE, the decisions from experience paradigm, 47 participants completed the experiment with compensation but no feedback in the actual game. The response variables we collected are the following. R rate. For each problem, the proportion of people taking the risky choice. Cohen's kappa, a measure for intra-rater reliability for categorical items. P agree is another cohort level agreement statistic, the value of which is equal to 1 if both observed and predicted choice falls on the same side of the random choice, that is 0.5, else 0. And finally, only in case of DFE, sampling duration, which is the number of samples a participant takes before committing to an actual choice with consequence. And here are the results. We calculated the completeness of CPT on different datasets first, and all the datasets are more than 90% complete on CPT. Here's the comparative result sheet for DFD. This here is our dataset, which gives intra-rater reliability for 2 subsets of our data, and correlation measures up to 0.78. As compared to the winning models in Techno Choice Prediction Tournament that shows correlation in excess of 0.9. This over here, Beast, is the winning model in a recent prediction tournament by Plonsky and team. Putting in perspective, here we see winning models are far more removed from the underlying variance in human choice behavior than the baseline models. Coming to decisions from experience, the baseline model is primed sampler with variability. This model predicts choice to be the option with maximum expected value of sample of size which is uniformly distributed. The upper bound of sample size is the only free parameter of this model. And here we see two possible predictions for the same choice problem. The winning model is an ensemble model which predicts choice as a consequence of one of the four rules listed here, thus explaining within person, between person, as well as between problem variability and a total of 12 parameters. And the results? The most interesting observation here is that despite baseline model is much simpler, it better respects the variability of the human choice behavior as compared to the much more complex winning model with more than 10 parameters. Just to reiterate, baseline models are more reflective of human choice variability than the winning models. And so these were the results of our study. Let me summarize our findings hereby. The above results, while on the one hand gives us a quantitative measure of limits of predictive accuracy in choice behavior under risk, on the other hand, it points to a more fundamental issue of using only quantitative measures in the model evaluation. The possible reason for such close fits could be just overfitting. The so-called better models were possibly fitting noise, and this also implies that the parameters found for one dataset might not be able to generalize well to other datasets. A more complex model, as we saw, is not necessarily a good model. Rather, a very simple baseline model, primed sampler with variability in case of decisions from experience, very elegantly explain the variance in choice behavior. Finally, we want to expand the study by differentiating between the sources of noise. Let me try and explain this. You weigh yourself back to back in succession. Any fluctuation in the weight corresponds to what is called a measurement error or response error, say caused by a fault in the machine or a change in the spring tension of the spring balance here. However, what we are more interested in is the change in weight before and after, say, eating an apple, which is what is called the process error or preference noise. We expect repeated measures under same setting after sufficient gap as formalized in our experiment would elicit preference noise. This has been further corroborated by Bhatia and Looms in their theoretical note, Noisy Preferences in Risky Choice. They show how if the underlying cognitive process is a single source of error, it can lead to systematic biases in the recovered parameters. And in short, we want to untangle the two sources of noise with our next study. Thank you. And any questions, you can email us.